This video will cover nonlinear relationships and how we use regression to estimate nonlinear relationships. So we're still in the world of linear regression, so we're still using ordinary least squares to estimate the coefficients in the regression, but we're going to model relationships that are nonlinear. There are many ways to do this. I'm going to talk about the two most common nonlinear relationships that you will encounter in applied research and applied work. So this is again, all of these examples are exaggerated. So this is made up data just to demonstrate the concept. These are not real relationships. When we look at real data, you rarely see things that are perfectly linear or perfectly quadratic or perfectly exponential. But these examples are exaggerated just to demonstrate the point. So let's say we have some two generic variables, y and x. So this is the dependent variable y, independent variable x. And if this is what the relationship between x and y looks like, we can clearly see that there's a linear relationship here. So anybody who looks at this, if you were asked to draw a straight line to draw a line that best approximates this relationship, you would choose a straight line. Okay? It's linear. So if we increase x by 1 unit, y tends to increase by some fixed amount. I don't know exactly what the relationship is. Here it is, 2.75 plus 5x. So the slope of the line that best approximates this relationship is 5. So if you look here, we go, for every 1 unit we increase x, y increases on average by 5 units. And notice that's true everywhere along this relationship, whether we're out here at 20, 15, 5, somewhere down here, 2.5, the slope looks to be the same. So when we model something using linear regression, and we write down a regression equation that has x in a linear form, so y equals a plus bx, that's we're assuming a linear relationship. So we're assuming, what we're really assuming there is that the slope of the estimated regression line is constant. Now we may encounter situations where the slope of the estimated regression line is not constant, or we have some reason to believe that the slope would change. So if you think back to your principles econ class, principles of micro for most of you all, and you think about increase or diminishing marginal utility. So as you consume something, the amount of utility that you receive increases, but at a decreasing rate. So in that example, the marginal utility would actually decline as you consume more of something. That first bite of pizza provides more utility on the margin than the 10th bite of pizza. So that's an example where things are not perfectly linear. So how much you expect the dependent variable, in that case utility, to change as you increase the amount of pizza you consume, pizza would be your x, it's going to change throughout that range. So that's an example of a nonlinear relationship. If you think about costs, we tend to think marginal cost increases as we consume or as we produce more of something. So there are lots of examples that are nonlinear, but this linear relationship is what we assume most of the time. So if we're looking at the estimated regression equation, y hat, again, that's the predicted value, a is the intercept, b1 is the slope, x is the independent variable. The slope of the line, that should actually say change in y hat over change in x, is equal to b1. So b1 is the slope. If we increase x by 1 unit, y hat changes by b1 units, and that does not depend on the value of x. If x equals 0, x equals 10, x equals infinity, that's the slope of the line. So for example, that relationship we had, y hat equals 2.75 plus 5x, the slope of that line was 5. And so again, that should say change in y hat over change in x equals 5. So here's an exaggerated example of a polynomial relationship. So what's different here than the first one, notice the relationship between x and y is nonlinear. So when x is small, increasing x causes y to go up, there's a point at which y is at about its maximum value, and beyond a certain value, if you increase x by a larger amount, if you increase x, y decreases. So this is a classic nonlinear relationship. And we would model this using a second degree polynomial. So if you were to draw a line that best fits this data, you would try to draw a line through the center of the points, and your line would look something like this. It would increase, it would peak, and then it would decrease. And we could model that with a polynomial. So we could write down y hat equals a plus b1x plus b2x squared, and that would give us this second order polynomial. And in this case, the coefficients that we estimated, 18.94 would be your intercept, and we don't have a slope the way we had in the previous example. You have to use a little bit of calculus to determine what the slope of the line is at a given point, but I'll show you how to do that on the next slide. But all we have to do, if you want to capture some nonlinear relationship where you have one critical point or one place with a maximum, you can include x squared as an independent variable. So if x is square footage of the house, you would include square footage squared as an additional independent variable. And that would allow your regression equation to capture this nonlinear relationship. So when you're writing down this regression equation, you have your y hat, that's your estimated value, a is your intercept, but now we have x and x squared as independent variables. Again, they're the same variable, x measures the same thing, we just include the square of x in the regression as well, and this will allow you to estimate a relationship between the variables that has one critical point, or a maximum or a minimum. If you think about the slope, notice it depends on the value of x. So if you're down here at x equals 5, the slope is positive. If you're over here at x equals 25, the slope is negative. If you're somewhere around 15, the slope is approximately 0. So when we look at the slope of the estimated regression line, it needs to depend on the value of x. And in this case, the slope of the line is going to be the coefficient on your x term plus 2 times the coefficient on this x squared variable, so 2b2, and then you multiply that by the value of x. And that is just the first derivative of the estimated regression equation. So for those of you who have had some calculus, all we're doing is taking the first derivative of that estimated regression equation. So in this case right here, we had 19 plus 27.6x minus 0.9x squared. We're going to bring down the 27.6 minus 2 times the 0.9 times x. So we get the 27.6 right here. 2 times 0.9 is 1.8. Again, we bring that negative sign down. So if we plug in values for x right here, so notice if we plug in x equals 5, we're going to get 27.6 minus 1.8 times 5. We're going to get a positive value because the slope is positive right here. If you plug in x equals 25 into this equation, you're going to get a negative number. And notice over here at x equals 25, the slope is negative. If you set this equal to 0, right here, 27.6 minus 1.8x, just set that equal to 0, solve it for x. That will tell you precisely the point where this estimated regression line is 0. And for those of you that have had a calculus class, that's exactly how you determine the critical points when you're trying to find the maximum or minimum of a given second order polynomial. So again, we're going to do all these in Excel, so I'll show you some more examples there. So here's another more exaggerated example, and this is when we would use the natural log of the dependent variable. Now you may be thinking, if you're familiar with the natural log function, it doesn't look like this. So if you had y equals ln x, that's not going to look like this. But here's a relationship where x is increasing slowly at first and then very quickly at the end. And this is what we typically think of with exponential growth. So if you're thinking about something that's growing exponentially, this is the type of relationship you might expect to see. So let's just think about an investment that earns 3% per year. So if you earn 3% per year, and that's compounded annually, you're earning interest on the interest. So you're getting 3%. Let's say you put $100 in some investment, you get 3% the first year. So at the end of year 3, you have $103. Well, the next year you're earning 3% on $103, not your original investment of $100. So each year the total amount that the balance changes increases over time. So it's always increasing by the same proportion, but it's increasing by a larger absolute value. So if you look right here, when x is small, this 3% increase, just for let me say what this is. Actually, this is much larger than that. So this is 87%. But even if we have something that is a high rate of return, if we have a low principal, the absolute growth in that account is going to be small. But eventually it starts to compound, and we start to see this very, very rapid growth in that account balance towards the end. If we're assuming this x was time, y is the future value of that asset. So this is very similar to y equals e to the x. So if you're thinking about exponential growth, this is what you're going to think about. This exponential growth right here, e. And that's a constant. So in this case, the relationship here is natural log of y, ln y hat. Again, you take it's the y hat. The hat goes over the natural log of y, not just the y in the middle, inside there. Minus 0.95 plus 0.87x. So even though this is very abnormal return, this would be the equivalent of saying if we increase x by 1 unit, our y is increasing by 87%. Right? So, and I have a slide at the end that shows you where this is coming from. So if you have some relationship where you think the dependent variable is growing exponentially, you can model that relationship using the natural log of the dependent variable. So if y is the portfolio balance, and it's earning some fixed percentage of interest, so you're earning 3% per period, say 3% per year. In that case, y would be the portfolio balance at a given time. X would be the time period, so it hasn't been invested for 1 year, 2 years, 10 years, 20 years. B1 would be interpreted as the percent change in y. We multiply it by 100, and that would be the percent change in y if we increase x by 1 unit. So anytime you have a natural log as the dependent variable, you want to multiply that coefficient by 100, and that's the percent change in y if we increase x by 1 unit. So in this case, we had the natural log of y. Ignore the constant right here. We don't really care about this anymore. I'm not sure why I keep clicking on that. But we would say if we increase x by 1 unit, y increases by 87%. So if we increase x by 1 unit, y increases on average, or y hat increases by 87%. And just to show you briefly where that's coming from, this is the form that we would have for exponential growth, where y is the dependent variable, a is some initial value, e would be that just mathematical constant, b would be, in this case, the rate of change, and then x would be the independent variable. So if we think about x as being as the time period, you can think about b as being the return, a being the initial investment, and y being the future value of that at any given time period. So if we take the natural log of both sides, and remember that there's some properties of natural log you may want to review. You don't need them for this class, but it may be helpful just to understand where some of this stuff is coming from. Take the natural log, we get a natural log of y. Anytime you have the natural log of a product of two numbers, it's the sum of the natural logs. So this is actually ln a plus the natural log of e to the bx. But ln e to the bx is just bx. So this is why we get this form where the natural log shows up as the dependent variable on the left-hand side when we think we have exponential growth. So it transforms that exponential relationship into something that's linear which is why we can estimate it using the methods that we already know. We can estimate it using least squares. If you try to model this relationship here, we cannot model that using least squares. It violates one of the assumptions. But if we transform it using the natural log, we now get something that can be estimated using least squares. This ln(a), we can just rewrite ln(a) as just lowercase a as our constant, which is why we write it in this form right here. If we were kind of going the other way and we're going to take this ln model back to this y, you would see that it works out. But we don't need to do that. But this is just a little bit of math showing you where that's coming from. And where you may be familiar with something like this, let me see if I can write on the, I'm not sure if I can write on the screen here. Let's just see if I can do this. So you may be familiar with this. Again, this is P. Sorry. This never works well. The future value equals P e to the RT. So this PERT. So if you have, we'll just make that present value. So if you have interest that's compounding continuously, this is how you find the future value. So if you invest PV at you get a return R and it compounds continuously, this is how you would find the future value of that at any given time. And notice how similar that is to this form right here. So you see this all of the time in finance. This shows up everywhere. And this is just a little bit of math showing you where that's coming from. But in terms of interpretation, I will show you later how we actually estimate these in Excel with real relationships where we might actually use these, and you'll get a feel for how to generate the variable or create the correct columns and then estimate these regressions.